started
Okay.
the recording.
Okay.
இதுக்கு முந்தின ஒரு பிக்சர் இருக்குமே, ஒரு ரவுண்ட் போட்டுக்கு இல்ல
இதுதாங்கய்யா ஃபர்ஸ்ட்.
ஐயா
இல்ல இதுக்கு முன்னா
ஃபர்ஸ்ட் ஸ்லைடுங்க.
இதுக்கு முன்னாடி
இதுதான் ஃபர்ஸ்ட் ஸ்லைடுங்க.
இல்லைங்கய்யா, ரவுண்ட் போட்டு கோர்ஸ் எல்லாம் காட்டுவோமே.
ஐயா ப்ளே பண்ணுங்க அந்த வீடியோவை, அதாவது பவர் பாயிண்ட, அப்பதான் அதுக்குள்ள வரும்.
That
இருக்குங்க.
picture is seen in the slide itself.
ஐயா உமா ஐயா எது சொல்றாங்கன்னு கொஞ்சம் கேளுங்களேன்.
இந்த ஸ்டேட் தான், அதை ப்ளே பண்ணுங்க.
இதுல நீங்க இது போட்டுருங்க, பிரசன்டேஷன் மோட் போட்டு. ஐயா ரைட் ஹேண்ட் சைடுல ஐயா இப்ப ரைட் சைடுல பாத்தீங்கன்னா ஃபோர்ஸ் எல்லாமே நம்ம சிஎம் சிஎஸ் ரேடியஸ் எல்லாமே இருக்குங்க.
இங்க எல்லாம் வரல, அங்க இருக்கிறேன். என்னதுல வந்து டெரிவேஷன் ஆஃப் நியூட்டன்ஸ்லாம் இருக்கு.
அதுல வந்து கம்ப்ரசிவ் பிரஷர் தான் நம்ம we are going to start with.
அதுக்கு முன்னாடி இருக்க படம் இல்லையே,
படம் ரைட் ஹேண்ட் சைடுல இருக்குங்க.
இல்ல நம்ம இதுல வரலையே. ஓ, ரைட் ஹேண்ட் சைடுல வருதா?
ரைட் ஹேண்ட் சைடுல இருக்குங்க.
ஓகே.
I think when you are seeing in the mobile, it will be a little bit small. That's where I think you are having some challenge.
இல்ல நான் படத்தை பார்த்துட்டேன். அந்த ஓகே, படத்தை பார்த்துட்டேன். ஓகே ஓகே.
But people who are in laptop, they can see very well. It is very clear here.
Okay.
Then we can go on.
Okay. So we will start.
Yes, Aya.
We will start with the picture. Friends, last class we saw the derivation of the mass formula for an object. If m is the mass, m equals beta times a into c minus r. That is the mass formula for an object. This formula has a very unique feature in the sense that this is the first formula we have where on the left hand side we have the mass which belongs to the universe, the mass. On the right hand side we have the parameters of the space. T is the space, R is the, all things refer to the space. So this formula links the massive parameter mass with the invisible R and C. In that sense, it is a very unique and important formula. And today we will see an application of this formula. As a first application, we take the derivation of Newton's law of gravity. Why derivation? Because Newton did not derive the formula, but he put the Kepler's laws in a mathematical language, that is all. So it is a translation of Kepler's laws into a mathematical language. So Newton, we can't say he derived it, we can say he deduced it. from Kepler's laws of planetary motion. And once he deduced it, people asked him, why don't you frame axioms and derive the formula? But Newton said, I don't want to derive the formula. I deduced it from Kepler's law. The formula works. That is all enough for me. The formula works even today, but there is no derivation for the formula from the first principles. And
who made a complaint? But you made a complaint, right?
And Newton, even though publicly Newton said that he is not interested in deriving the formula, privately he was trying to derive by putting some axioms or introducing certain new ideas. He was trying to derive the formula, but he could not. And 30 years after Newton came a scientist by name Lee Sage. Lee Sage modified the Newton's concepts which he gave to derive the formula. And Lee Sage also tried to derive the formula, but he could not. So the challenge was there in physics to derive Newton's law from first principles. Then after Lee Sage, many stalwarts, somebody like Richard Feynman, a great physicist, Richard Feynman tried, de Broglie tried, and so many stalwarts tried to derive the formula, that is G m1 m2 by r square. They all got the r square term, but they did not get the mass term because they did not define what is mass. So the challenge is there even today to derive Newton's law. So we thought, now that we have got a mass formula, the formula for mass, why not we try to derive Newton's law from our mass formula? And it so happens that the formula gets derived. So 300 years of challenge is taken here, is met here in a very successful way. So now we present to this audience the derivation of Newton's law of gravity. This is a very historic moment because it is a historical derivation. If I go back, once we started taking Maharishi's concepts into science, it was about, we took about 4 or 5 years to get the mass formula, and another 4 or 5 years to get this derivation. And in all these, about 10 years of work, and Arunidhi, Uma was actively engaged, and thanks to her initiative and her intuition that first we got the mass formula and then the derivation also. Now we start the derivation. When we go along with the derivation, halfway through, we stop and we give some time for discussion, and then we continue the derivation. So the derivation starts. We are having a solid body indicated by M. In the picture, there is a solid body. M is placed there. Once M is placed there, the space, according to our axiom, the space converges and finally gives a pressure on the surface of the body. That you can see the arrow marks. The space converges and finally gives a pressure on the surface of the mass m. Okay. Now in the picture, Tm represents the pressure given by the space on the mass m. This is a C means compressive pressure. M denotes here it is a pressure on the mass m. So Cm is the mass, Cm is the pressure, compressive pressure due to space on the surface of the mass m. Keeping that, now we come to a question. Okay, the question is, at a distance small r, we consider a point. At a distance small r, let us say we consider a sphere of radius r. Then on that sphere, the imaginary sphere of radius r, on that sphere, we take a unit area. So due to the convergence of the space, what will be the pressure, the converging inward pressure on the surface of the imaginary sphere? That's the question we raise now. Because the space is converging. When it is converging, we consider an imaginary sphere of radius r, and on the imaginary sphere, we take a unit area. How much will be the inward pressure on that unit area taken on the surface of the sphere? Now, as the picture shows that whatever the total force entering the sphere, the outer sphere, the whole total force will come and act on the surface of the body. So the total force acting on the surface of the body of mass m will be the same as the total force entering the sphere. Whatever enters the sphere will finally come and act on the mass m. So on the mass m, what is the total force acting on that? On the mass m, area of the sphere of mass m, let it be capital A. So Cm is the pressure. The area of the sphere, the surface area is capital A. So A into Cm will be the total force converging on the mass m. This total force, ACm, is coming through the outer sphere. So what will be the pressure on the outer sphere? Let us say the Cs. What will be the value for the Cs, the pressure on the outer sphere? The total force entering the sphere is A into Cm. Okay, whatever enters there comes to the mass. So on the mass we have ACm. So this total force is coming through the sphere. Then we know the total force entering the sphere. Then what is the force per unit area? Then we have to divide the ACm by the surface area of the sphere, 4 pi r square. So A into Cm divided by 4 pi r square will be the pressure on the surface of the sphere, which we have denoted by Cs. So we must be very clear of the notations here. The space is converging finally on the sphere, converging. And on the sphere, it gives a force of the total force of A into Cm. This much force enters also the outer sphere before it arrives at the mass. So at the outer sphere, what will be the pressure? The total force entering is A into Cm divided by the 4 pi r square, the area, that will be the Cs. Now that is what we have indicated here. The total force entering the sphere of radius r, that Fs, 4 pi r square into Cs. This is a total force. This total force how do we find? The ACM is the total force entering the sphere. ACM divided by the area of the sphere, 4 pi r square. So that is the pressure on the surface area of the sphere. So Cs equals A into Cm divided by 4 pi r square. This is one equation we get. So again, I will repeat. Cm is the compressive pressure on the surface of the body, object. ACM is the total force compressing the body. This total force ACM is passing through the whole sphere of radius r. It is passing through. So on the sphere, on the imaginary sphere, the pressure will be, the total force entering is A into Cm divided by 4 pi r square, the area of the sphere. That will be the inward pressure on the surface of the sphere. But on the surface of the object, the pressure will be Cm. Therefore, now we have to be clear, we have to understand clearly this particular equation, Cs equal ACM divided by 4 pi r square. This is the beginning of the derivation. Now, let us give some time for a discussion. Any doubt regarding this particular equation? Cs equals ACM by 4 pi r square.
Vijay sir, you can ask a question, sir.
Dr. R, if there was no object M, now how would you then define the existence of a compressive pressure?
If there is no object M, if there
Right.
is no object M, there won't be a compression developed in space converging towards a particular thing. That picture will not be there at all. There is
Okay.
nothing to converge upon.
Right. But the compression itself is inherent as a property
Compression?
in the compression property itself is inherent within that space, but it doesn't become active unless an object is there.
Now, because our definition is space has a property of compressing the object.
Okay.
It has a
Okay.
property of compressing a system, acting
Right.
on the system. So the system must be there for the
Okay.
surrounding pressure to act.
That's right. Okay.
Okay. Okay. Thank you.
Aya, what could you talk about the sphere in the concept here? Like, why do we have that sphere around the mass? I want to understand a bit more about that.
What, ma?
I want to understand the relevance of we considering sphere in this concept. Like there is that mass and we have a sphere. I want to understand the relevance of sphere in the discussion.
Because Newton's law deals with the force between two spheres, two masses. So we are going to derive Newton's law. So first we have one mass, see the consequences, then place a second mass, see the consequences. Finally, the equation will be derived. Because Newton's law, you need two masses. He speaks the force between two masses. So that is why we have to consider the first mass, its consequences, then place a second mass, and then what happens? Finally, we derive the formula.
Ma'am, actually, the idea is we are keeping a mass in the center and we are trying to go away a distance r and then seeing what is the property over there. That is the imaginary sphere that we have considered. And then on that position, we will be placing another sphere. This will come in the next picture. You can understand that.
Okay. Okay, thank you.
Thank you, ma'am. If any other question, then we'll proceed further.
I think we can proceed now, Nia.
Okay. So we go to the next one. What is the next one, ma'am?
Repulsive pressure. Yeah.
Okay.
Yeah.
It is not clear. Can you give a screenshot?
Yeah, the repulsive pressure is there in the screen. You can see that.
Screen la na edo sotam poiduchu. Can you put it here?
Hope we have to do something. Come back. பின்னாடி வந்து பாருங்க.
ஆமா. ஒரு படம் வந்து மறைச்சிக்கிருச்சு அத.
What picture ங்கயா அது மறைச்சது?
எழுத்து வீன் வந்து மறைச்சிக்கிருச்சுமா. ஒரு எழுத்து வீன் வந்திருக்கு.
Oh, yeah. Okay.
Dual left scroll பண்ணுங்க.
ரைட்ல படம் வருது, அது மேல எம்னு ஒரு எழுத்து உட்கார்ந்துட்டு இருக்கு. ஓகே, இப்போ கொஞ்சம் பரவாயில்ல.
ஓகே.
எம் கொஞ்சம் வி கொஞ்சம் மேல போயிடுச்சு. அந்த எழுத்து வராம பண்ண முடியுமாமா? எம் வி இதெல்லாம் வருது.
இல்ல அது ஐயா அது எல்லாமே இமேஜஸ்ங்க. நீங்க லெஃப்ட் போனீங்கன்னா இது வந்து பிரசன்டேஷன் வந்துருங்க. If you go left you will get the presentation.
இல்ல அந்த படத்து லெஃப்ட்ல பிரசன்டேஷன் இருக்கு. படத்து மேல இருக்கேன்னு பாக்குறேன். வேற வழி இல்ல. சின்ன ஒரு செல்போன் தானே. வேற வழி இல்ல. Okay, fine.
I think if Aya clicks on view, then he can put what he is referring to as M and V are participant names. He can push that aside if he clicks on view. Aya,
okay.
you click on view and then you will see it as side by side or standard.
சரி, இப்போ கொஞ்சம் பரவாயில்ல. காம்ப்ளிகேட் பண்ண வேணாம். இப்போ கொஞ்சம் பரவாயில்ல. ஓகே, இப்போ அந்த பிக்சருக்கு வந்துருங்க. Okay, we proceed further.
Okay.
We proceed further. Now, we place the object M. And so far we discussed the action of the space. Space is compressing on the object. Okay. When it is compressing on the object, at some distances also, it will give them some pressure, and finally it gives a pressure on the object. So we calculated that pressure at a distance from the object, pressure at a distance, that as the distance becomes closer and closer, the pressure goes on increasing, reaching maximum on the surface of the object. Leave it. Now, let us see the effect of the repulsive force. We are going to discuss the repulsive force from the object M. Because M consists of fundamental particles. Each particle by rotation produces waves. So out of the object, the waves are coming out in all directions. So they constitute the kind of a repulsive pressure, which we have denoted by Rm, a repulsive pressure.
Hello?
R suffix M. Now, what is the
presentation நடந்துட்டு இருக்கு?
You proceeding? I am muted.
Okay. Now, Rm is the repulsive pressure from the object. Then, what is the total the repulsive force? Total repulsive force coming out of the mass M will be area A, capital A into Rm. So A into Rm is the total repulsive force coming out of the mass. This repulsive force is passing through the sphere. So on the sphere or through the sphere, which we are considering the imaginary sphere at a distance r, A into Rm will be passing through the sphere. So now the question is, what will be the repulsive pressure passing through unit area of the imaginary sphere? Then the total force passing through the outer sphere is A into Rm. So that total force divided by the area of the sphere 4 pi r square. That will be the repulsive pressure on the surface of the sphere. So now, on the surface of the sphere, on the unit area, there is a compressive pressure due to space. There is a repulsive pressure due to the mass. Therefore, now, what is the net compressive pressure at a distance r? That will be Cs is the compressive pressure minus Rs is the repulsive pressure. So the difference will be the inward pressure. That is what we have written on the left-hand side. So Rs equals the total repulsive force coming out, A into Rm, divided by, it is acting on the sphere of radius r, so divided by 4 pi r square will be the radiation pressure, repulsive pressure on the surface of the sphere. So, what is the net compressive pressure? The net compressive pressure will be Cs minus Rs. Now, Cs we are supplying, Rs we are supplying, and we are rearranging. We take the A by 4 pi r square common outside, Cm minus Rm. So this is a crucial sentence. The net compressive pressure due to the space, there is a net compressive pressure. The value is A by 4 pi r square, Cm minus Rm. Okay?
Any questions? So first we saw compressive. Now we have also saw the effect of repulsive, compressive, and the net formula at a distance. So is there any question until now? Okay, yeah, we can proceed.
Okay, ma'am. No, you go to previous, yeah? Previous. Okay, stop there. Now, Cm minus Rm. So we are using now the mass formula. What is mass formula? M, the mass of the object M equals beta times A into Cm minus Rm. That is our mass formula. So A into Cm minus Rm becomes mass M divided by beta. So that is what we substitute from the mass formula. So after substituting from the mass formula, here we get next. Yeah, next one here. Okay.
Yeah.
The mass formula is M equals beta times A into Cm minus Rm. Using this, we write A into Cm minus Rm equals M by beta. So we have here M by beta 1 by 4 pi r square. This is the net compression. Net compressive pressure is this. Now, at that point at a distance r, we are placing the second ball. We are placing the second ball at a distance r of mass small m. So that mass we are placing will offer an area for the compressive pressure to act. It will offer an area. How much area it will offer, that mass small m, we do not know. It depends upon the position in which we are keeping that m. So in general, we assume if m is the mass of the second one, small m is the mass, the area offered for the compressive pressure to act is mu into am, mu into m, where mu can be anything. It may be 0.1 or 0.2 or 0.3, some factor. So this is the area offered by the second mass. So what is the force on the second mass? M by 4 pi r square beta is a force on unit area. This is a unit area multiplied by mu m, the effective area offered by small m. This will be the total force on m. So the total force on m we have determined, that is equal to what? This is, so here m we keep, capital M we keep, r square we keep, mu is up, 4 pi beta is here, mu by 4 pi beta we keep as a constant g, then we have g m by r square, where this g is our gravitational constant. So finally, we get the formula g mm by r square, and that is Newton's law of gravity. So finally, we are able to get the Newton's law of gravity derived. The point is here, we are getting m. It is because of our mass formula. If we don't have the mass formula, we cannot bring the capital M inside the picture. We are able to give the capital M inside the picture because of our mass formula. So the mass formula is all important. And using that as an application, we have derived g mm by r square. Now, any clarifications or doubts?
Yeah, why the significance of saying, hence the inward force towards capital M acting on area mu M. So is it because the object represented as capital M is bigger than the object represented as small m? That is why it is inward force?
No. Even before you are placing the small m is only indication. It's not that this is smaller. You can call it that one m1, this one m2. Even before placing the second mass, there is an inward pressure.
Yeah.
The inward pressure is m by 4 pi r square beta. There is an inward pressure even before you are placing the mass.
Agreed.
Once we place the mass, this offers an area to act. This
Okay.
is on unit area. This is offering an area to act. This may be 5 square or 10 square. Then what is the force on this? Area offered multiplied by the pressure, unit force per unit area. So we multiply to get the total force.
We have one more question. Even in general relativity, Einstein's brings this. Yeah, can you hear me?
Yeah,
Are
can
you
you be
familiar?
yeah,
Familiar?
loud here.
Yeah. Okay, I'll be loud. So even in general relativity, Einstein brings this term G on the right hand side. This is when he describes the stress energy tensor, he adds this 8 pi G by C square term at the front. And there is no clarity of why Einstein, who relies on slope of space-time as gravity, would bring G in there. That is the first question I have.
Okay.
Secondly, by bringing G, is here G actually refers to the compressive pressure, right? So is he actually, although he did not know that there is compressive pressure, is he incidentally bringing a term that corresponds to the compressive pressure? That's the second question.
Okay. Now, the question is very relevant because Einstein purposely brought somehow the factor G because he wanted his equation to reduce to Newton, and as a special case. As a special case, he wanted his formula to reduce to Newton. So if he wants to his formula to reduce to Newton, he must have the factor G there. So purposely he brought the factor G there. So that under special circumstances, his formula, he will say, will reduce to Newton, so I am all right. As a special case, I am getting Newton, so my whole equation is all right, he can claim. So he purposely introduces G there. But for us here, G comes as a natural one. For us, you know, G is mu by 4 pi beta. This is what we call G. So here we are not introducing G. It evolves from our formula. Mu by 4 pi beta is G. So there's a lot of difference. Here G evolves from the derivation, whereas Einstein introduced that so that as a special case, he can get Newton's law.
Okay. I have some more questions, but I have to refine my questions a little bit. So maybe I will ask you later.
Okay, further question maybe post. Any further question, okay.
Hello. Yeah.
Sir, I have one doubt.
Okay.
Sir, I'm Daumani here. I have one doubt actually.
Yeah. Please
Hello?
proceed. Please proceed,
Yes.
Sir, this 4 pi r squared you are putting as area over here, no?
Yeah.
Sir, 4 pi r squared is the total surface area of the sphere, correct, no?
Of the imaginary sphere we consider. Okay.
Correct. But actually, whenever you talk about an area to be multiplied by pressure for the sake of obtaining a force, that area cannot be total surface area, because if the pressure is exerted from one side, then the other side becomes ineffective. So normally we call it as actually the shade of the image, or otherwise a cross-section area. That is how we normally consider, excepting the drag force or something like that. That drag force matter comes into picture only when it is a flow past immersed bodies. Correct? No, in fluid mechanics. We call it as
Okay.
flow past immersed bodies, where actually
Okay.
a spherical ball is running through a stream of liquid, where
Okay.
the liquid is going surrounding the whole body. So entire 4 pi r square is in contact. So you can
Okay.
consider that whole area. Otherwise,
Okay.
that area to be considered must be actually the effective cross-section area only. How here it is 4 pi r squared is my doubt.
Okay. 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 Can
I-
you please come to our picture, first picture, please.
Especially the axiom.
முதல்ல அந்த first picture எங்க first page போட்டீங்களே அந்த picture. You see here, the imaginary sphere is not moving. It's not a mechanical one.
Yeah.
It is at rest.
Yeah.
It is at rest. There is a force in all directions. All possible directions, the force is there. So it is acting over the whole area of the sphere. The whole area.
Yeah,
Of the
okay.
sphere.
Okay.
So the whole area is how much? 4 pi r square.
That is correct.
So multiply by 4 pi r square the pressure to get into the total grip, total thrust on the sphere.
Okay.
That's all. We are
Yeah,
multiplying.
actually, this comes from our axiom. Our axiom considers surrounding compressive force, not
That
in a cross section.
Yeah, correct. That is for that particular mass. Whereas now we are talking about an interaction between that bigger mass to a smaller mass. No.
No. That comes afterwards. First, we establish CS first.
So
When
how can we
establish
apply the
equation-
same? How can we apply the same formula for that? Somehow I'm not comfortable with that.
Even for that,
Okay.
any mass in the space is exerted by the surrounding pressure space. So
Okay.
even for the, irrespective of the size and the parameters, even that mass is going to experience that surrounding compressive phase. After deriving that CS and RS of individual mass, in the third one, we are saying the relativistic approach between these two mass. So the C applies for both the mass according to the axioms.
Sir, I will explain you, sir.
Yeah, please.
This is the compressive pressure they have taken as 4 pi r square is the imaginary sphere, and secondly the repulsive pressure, and the third one is we are trying to keep a mass small m on a point over the imaginary sphere. Now the question is we are talking about the effective area offered by the small mass m. So that is what we are. That is a unit area. Your question is right. The whole sphere cannot act on small m.
That is what I'm asking actually. So
Yes,
how can you put that 4 pi r square?
We have
That is
actually
not-
skipped some more steps in the between, so that only the confusion happens. Whenever you keep a small mass at a point m, we are considering an effective area on the small mass, sir.
Okay. Yeah.
That effective area is mu times m he has taken. Let mu m be the effective area offered by the small mass m. On that effective area, he is calculating the force, the inward force.
All right. Okay. Got it. Okay. Nice. Yeah, nice. Please go ahead.
Thank you, Aya. Thank you, Aya. Thank you.
I have one more question. So if you look at this for mass formula m equal to beta equal to Cm minus Rm, and if you try to apply that to, let's say, black holes, where the Rm could go to 0, can we claim that all of Cm is acting on a relatively small a, and therefore mass goes to infinity? Can we claim something like that if you apply it to black holes?
No, we are not right now talking about the black hole situations. So there is no discussion at all about the black hole here. That's a different subject. But here in this what we have told here, in this situation, in this derivation, if we have anything discussion, we can have it now. Because let us finish the derivation first. Because black hole situations, we are not coming, we are not discussing now, right now here.
Okay.
Dr. R,
Yeah.
one question.
Yeah.
This gravitational, the capital G, what is coming out of this derivation? Can you just say a few words? How is that different than the gravitational constant that is normally used in the Newton's law of gravity?
Yes. In Newton's law of gravity, okay, in Newton's law, G is simply taken as a proportionality constant, the G. He doesn't have a physical situation of explaining what is G. G has a proportionality constant, that's all he has considered in Newton. In our case, G has a structure inside that. Mu is there, divided by beta is there, and this mu, okay, this mu times the mass m is the effective pressure. So that mu, okay, cannot be a constant.
Right.
It varies from situation to situation. That mu, how do you place the mass? How much is the mass? So that mu is a variable. So in our case, G cannot be a universal constant.
And that is the value of the derivation, the insight the derivation has provided, rather than the empirical fact.
Yes. G cannot be a universal constant, as Newton claims to be. It depends upon mu. Mu depends upon the position. How do we place the object? So that is a significance of our G. Because we could have used some other symbol, but since G has become familiar and famous, we are using the symbol G, that's all. But our G has got a more meaning.
Right.
It is not simply the proportionality constant.
Correct. Thank you.
Thank you for the question. Thank you. Thank you.
Can we consider in one way, very in a gross way, or the way the Newton has assumed the thing is, on a mass, the compressive force on a mass is the gravitational force within that particular thing, like how the acceleration due to gravity is there for Earth, no? So like that. So so the thing is, it is drawing every object on the Earth, correct? No, towards the Earth. So that is what is this. See, same way, all the other objects outside also will attract the Earth towards it. That is what is the repulsive force. Actually, this is what Newton himself has considered.
So for Newton,
So correct. No, so now in that way, that mu by m, mu by beta, he has also taken, but somehow he has taken it as a constant because of the large distance and the effective cancellation of forces between many objects in a celestial level.
Okay. ஐயா நீங்க தவமணி தானே தவமணி பேசுறது?
ஆமா சார். ஆமா.
Very good. Thank you, ஐயா. Thank you for the clarifications you are seeking. Now for Newton, Newton did not bother about the cause for the gravity. He did not bother about. He didn't even say that the first body attracts the other. He didn't even say that. What he did is that he had the Kepler's laws of planetary motion before him. Kepler's laws are there. He translated that laws into mathematical equations. He deduced the formula. Now asked afterwards, people asked him, are you saying the particle attracts any other particle? He said, no, I am not saying that. I do not know what is the cause of gravity, but I know that there exists a force between two particles. And he says it could be one of the following reasons. The force between the two objects is there. The force could be any one of the following reasons. One, first particle may actually pull the second particle. The second possibility is that the space surrounding the two particles may compress it, even then they will come together. Which one is really happening, I do not know. So he did not commit whether the particle is attracting the particle or whether the space is compressing them. He did not commit. Without committing that, he got the formula because he deduced it from Kepler's laws. His platform was Kepler's law, not the cause of gravity.
Correct. That's right, actually. But if we say so, actually, then so far, whatever calculations are done to estimate the gravitational constant as well as acceleration due to gravity in the moon and in the celestial space, all those things are now being used for all the experiments as well as the real rocket science and everything. So how is it matching if that is not right?
Now again, the formula is the same. F equals G into m by r square. The same formula we also derive. We don't find with the formula. We don't find with the formula anything wrong. The formula is right. But what we claim is that force G into m by r square, that force is caused by the space, not the particle attracting other particle. That's what we claim.
Very, very nice. Very nice. I agree. If you say so, then the formula cannot be having the factors like mass of body 1, capital M, mass of body 2, small m, the distance between them, r. If that is there, we cannot say it in the other way. No, sir. That's actually, this says very clearly that it is between these two bodies only. Nothing beyond it. Once we could reduce a formula, let us assume actually the problem comes only when you assume there is a compressive force or there is a force beyond these two bodies which is pushing these two bodies towards each other.
Exactly.
Let us assume.
Exactly.
If that is assumed, then there must be another factor beyond these two bodies. Whereas the factors in this formula are body 1, capital M, body 2, small m, and the distance between only these two, nothing beyond that. That is all. Once that is there, where is the question of considering? You are also finally resorting to between these two bodies only. We are not. That means you are subscribing to the theory. You are subscribing to the theory that any two bodies attract each other, which is inversely proportional to the square of distance between them. That's what very clearly you are accepting.
Only one
if you are
change,
accepting
sir.
the second theory,
one change. Amma, please. One change, ma. One change. I'll say. One change. We will say not attraction. The force existing between the two bodies. The force existing between the two bodies is equal to G m1 m2 by r square.
Correct.
But we will say the force is caused by the space. It is caused by the space. Magnitude, if you want to find, G m by r square. The cause we are differing. It is not the particle attracting that. It is the cause of the gravity is the space compressing them. The cause is different for us.
So just to
but still G becomes constant only, no, sir?
That's what again we have.
That's a difference here.
In our case, G is mu by 4 pi beta. in our case. But it is a constant only for the situation, not universally. Because mu depends upon how do I place the mass, the orientation, so that it offers how much area for the pressure to act. So it is not a universal constant. It is a constant for the situation. That's what we differ from G. But Newton introduced G as a proportionality constant. He introduced simply as a proportionality constant. He did not have any elaborate situation for G. And in fact, he did not even know what is the value for G. Only after 100 years of Newton, the value for G was determined. After 100 years of Newton. He did not even bother what is the value for G. But he could explain so many things. He is great, really great. Only thing is we are changing the cause. We obtain the same formula. Newton is really great. He got the formula. When people approached him to derive the equation, he said, I am not proposing any axiom for the cause of gravity, but I have a formula. The formula works, that is enough for me. Hypothesis non-fingo is the Latin word. Non-fingo hypothesis. I don't want to form hypothesis. So in the cause of gravity, he did not commit, but the formula, he got it. We are adding that formula is the same, but the cause is not the particles, the cause is the space compressing them. So space comes very active now. In our whole science, we are bringing space into a very active one. Whereas in Newtonian case, space is simply vacuum. They did not bring space as an entity, but we are bringing space as an entity. So there's a lot of difference between the cause. But formula is the same. Even today it works.
Sir,
Thank you, Aya.
I'm actually Davmani's son, actually. I'm a student, Master of Science student, actually. I have one small follow-up question.
Sir, I told my son also to listen to this. Yes, come
exactly.
Now.
Thank you, Aya. Thank you. Thank you.
So, is there any situation where this G is other than the value that we have globally accepted, that is 6.7 into 10 power minus 11?
Yeah. Your question is very nice. Hello?
Yes.
Aya?
Sir, please tell, sir.
You will be getting a Nobel Prize. I'm telling now, provided you do this experiment. Provided you do this experiment, you will be getting a Nobel Prize. Look here. You take 2 cylinders. Okay, you take 2 cylinders. Okay? You suspend them, the 2 cylinders, so that the end is facing each other. The end is facing each other with a distance r. You find the gravitational force between the cylinders. Second experiment. You suspend the cylinders so that the surface of the body, the long surface, is facing each other, not the end surface. The surrounding surface is facing each other. You find for the same cylinder what? The force between them. The force between them will be different according to us. But according to Newton, he will tell only the mass that matters, so it will be the same. But for us, the area that matters. In the 2 cases, the area is different. Mu m is different. How much area they are offering for the force to act. In our case, it is different. Therefore, if you do 2 experiments, if the force in the 2 experiments, you will confirm that the force is not the same. So the force does not depend merely on the masses. It depends upon mu also. So G will change that. You do this experiment, you will get a Nobel Prize.
It is something like a magnetic flux rather than actually only a gravity. See, this type of theories are coming under that magnetic flux. Where the magnetic flux towards the bottom of the cylinder is different from the surface, curved surface.
No, but actually, by now currently we have launched many rockets, right? we have used only the Newton's law of gravitation principles
Yeah,
and
yeah,
all.
yeah, yeah.
So when the rocket is actually getting launched, when it is in propulsion, the surface area is different. The minute when the propulsion is turned off, when it tilts, right, the rocket, once it has gone outside the Earth, then the surface area is different.
Yes.
That is facing towards the Earth.
Yes.
Now, technically, according to their calculations, it should be wrong.
No,
But
no,
how
no.
have they accurately
yeah,
predicted
The
the trajectory of that rocket?
Sir, the point is, while the rocket starts leaving the Earth's gravitational field, the bottom surface would be the one facing here. Whereas once
Yes.
it goes to the space, actually, it is the cylindrical surface that we facing. That is what is the point.
Exactly. But with the mass here, as the sun's mass, with a distance here, relatively cosmologically small distance, the difference will be extremely small to detect. That's a problem.
I see. That is valid. Yeah.
That is valid.
One
That is
more,
valid.
one more.
That is valid. You are right.
You must take such a sensitive experiment because there is a Nobel Prize for that.
Oh, very good, sir. Then are we going towards a correction on G, which itself is actually to the tune of 10 to the power of minus 11?
Yes, yeah, exactly.
The value of G
right.
is already somewhere around 10 to the power of minus 11. Are we working out to make a correction of that, which will be somewhere around 10 to the power of minus 20, 10 to the power of minus 25? So, really, is it necessary, sir? Or what effect it is going to make?
Yeah, see, practically inside the solar system, the variation of G will not affect anything because, as you say, already it is only 10 power minus 11. So whatever slight variation, it won't affect the practical values. It won't affect. But the cause of gravity, we differ from Newton. We differ from the existing view vastly. The cause of gravity. The cause of gravity, cause of gravity, cause. It is that it is not the particle attracts another particle. So in all the textbooks now, what it says, they are misquoting Newton.
Yes.
They are misquoting Newton. Newton has never said so. He said, I do not know. But here in the textbook, they say Newton's law of gravity. Every particle attracts every other particle. It is totally wrong.
Fantastic.
Newton never said so.
Fantastic finding.
There exists a force.
I appreciate your efforts, sir. I appreciate your efforts, sir. Very nice. Very nice. Okay.
Thank you. Yeah, thank you. There exists a force between two particles. Good. But what is the cause? That's a different.
Sir, but the only way where you can tell that it is completely wrong is when
he's not telling completely wrong. Actually, you consider this factor also.
Okay, I see.
So now eventually it gives you a third principle. First principle, first concept is there is a mutual force of attraction between two bodies.
Okay.
Second hypothesis is whatever sir is telling, that is there is something external which is pushing these two towards each other. Okay. There can be a third one. There can be a third one, which is a combination of these two.
Yes. As you are really rightly thinking, when we go for the absolute cause and we are able to know hypothesis that may give a new way of a new invention out of it, and there could be a new impact out of it. So that's the attempt IA is making. And thanks for this wonderful discussion. I just want to give an heads up on the timing also. We are already ahead of time.
Sorry, we have taken out a lot of time because somehow. Thanks a lot.
Now this is
Thank you very much.
This is really fruitful. The goal of this meetings is for this wonderful discussions and vast thinking for all the participants out here. Actually, we are not done with the agenda. Maybe we will continue with the next meeting, or how should we do, Aya? It's already been time.
Now we will repeat it in the next meeting also.
I'm extremely sorry. Sir, if we have delayed the proceeding. Sorry.
No. I must thank you for all the clarification you are giving. Nicely, you are giving all the clarifications between the existing theory and our theory. Thank you very much, Aya. Thank you. This is what we expect. This is what we expect.
Exactly.
I was bit over enthusiastic with my son because he has come only yesterday from there, US. He is going to continue his PhD there only. I compelled him to sit with me. He's going to continue his PhD in University of Michigan, sir.
Very good, very good. Best wishes, best wishes.
Thank you.
Very
Thank
good,
you
very
very
good,
much,
very good, very good. So next week, next meeting also we will emphasize the derivation. We will once again revisit the derivation because it is all the more important one as an application of our mass formula.
Sir, I did not get any message at all, sir. Please take care of my request.
Can you please send your email ID in this chat window immediately?
Sure, sure.
Yeah, sure.
Okay. Great, thank you. That will be taken care. Thank you so much for your participation. Next week we will have exciting deduction, not derivation from for Newton's law of gravity, and also following up discussion on the derivation made by Dr. Alagar. Is there anything else you want to? Is there a pressing thought in your mind? You can speak up, or else we can conclude.
Yeah, let me add a small summary, ma'am. Actually, the idea is, as we said, we are starting with the space, its compressive nature towards the object. The Newtonian theory, not Newton. The Newtonian theory puts the arrow mark between the two masses. We are putting the arrow mark outside the two masses. That's all. And the concept is the same. And secondly, we all know that Einstein is another great theory which he has given with reference to relativity. He is also speaking gravity, but in a different way. So he has included the concept of space within it, and that will be still impressing if we are accommodating our concept with that. That is going to come in the next classes. Thank you.
Okay.
Thank you, Aya. Thank you, whole team. I would like to just add on. I'm very happy. Please don't feel sorry to give your questions because I don't understand anything. Only with the questions I'm able to understand. So please add questions. If we want, we can extend at least by 30 minutes next session if needed. Okay, we can plan ahead. Thank you so much, Aya.
Thank you, Ma.
Thank you, Aya.
Thank you.
Just one more thought from my side on the experiment that you talked about.
Yeah.
I think if you look at Einstein's general relativity, between a
point... Aruna, your voice is low. I don't know, it's only for me.
No, it is low. Yeah.
Laptop speaker, is that better now?
Now much better. Thank you. Thank you. Go on, please.
Hello, am I audible?
Yes,
you are.
Hey,
Aruna, go on. We are able to hear you now. I think some problem with his connectivity.
Okay, no worries. We can continue the same question from the next meeting.
Okay.
Thank you.
Am I audible now?
No, it's very feeble.
Yes, audible.
Yeah.
Okay. Maybe just one thought or a question. So the experiment that Aya was talking about, I mean, the answer can be given in the next session, but it's just a thought. It's a good, I think it's an important thought to be put in.
Okay.
If we approach that experiment of two pointed surfaces facing each other versus the sides of the cylinder facing each other, the curvature of space-time in Einstein's theory would differ. And as a result, I think even with general relativity, we will get two different gravitational attraction values. I think so.
Yes, sir. You are right, sir. You are right. Because relativity has more to do with the geometry of the object than the force between them. Definitely, that will help us to come out with the exact values.
Exactly. So the point is, even in that experiment, there is a necessity to differentiate the theory from Einstein. It's just a thought. Maybe we can look at it next time.
Okay. Yeah. Good, yeah, good.
Tamani, I sent you the invitation to join the group, and thanks for all your participations and questions. And let's meet, and we will keep posted about the next meeting timing sooner. Thank you so much.
Thanks a lot, madam. Thanks a lot.
வாழ்க
வளமுடன்.
Thank you all.
Thank you for the participation. Thank you all for the participation and nice clarifications and questions. Thank you. This is what we expect. Vijay, வாழ்க வளமுடன். Thank you.
வாழ்க வளமுடன், Dr.
Thank you. Thank you. Thank you.
Thank you, ஐயா. வாழ்க வளமுடன்.